Hello everyone, my name is Jinwook, and I'm presenting work done in collaboration with Bhoram Lee and Daniel D. Lee. This video introduces our paper on constrained sampling-based planning for grasping and manipulation. The grasping and transport problem in a complicated environment is a difficult task in motion planning. When choosing a grasp pose, we have to consider reachability and collision during arm motion planning along with a grasping score. Another issue is how to determine the optimal grasp pose among many redundant solutions. Next, for the transport motion planning, we need to consider many kinds of constraints. For example, we need to conserve the end effector's orientation while avoiding obstacles. Moreover, the target end effector in the task space is usually given as a position without specific arm configurations. In order to deal with these issues, we suggest an integrated planning algorithm for grasping and manipulation with constraints. First, in order to choose the grasp pose, we suggest a new concept called the planning margin. The planning margin is a spatial margin for the manipulator to be fully dexterous within the joint limits while avoiding obstacles. Among infinitely many configurations for the grasp pose, we select a best grasp pose maximizing the planning margin along the approach direction, which is obtained by introducing a parameterized intermediate pose, as you can see here. Next, for the transport task, while maintaining the orientation of the end effector, we suggest sampling in the task space and then finding the corresponding configurations in C space. Our method penalizes the motions that violate orientation constraints of the end effector. Common constraints can include keeping roll and pitch at 0 during transport in order to keep the object upright. This approach is efficient and fast since the corresponding configurations are found based on an optimization with soft constraints. We evaluated our method under various experimental settings using both a simulator and a real system and found it to be 3 times faster than traditional approaches. This sample video shows the experiment on a real humanoid robot. As you can see from these figures, it is obvious that our MPM RRT is faster than traditional RRTs for grasping and transport. We compared it with traditional planners such as JT-RRT and ICRA. If you have further interest, please see me during the interactive session and we will discuss it together with full experimental videos and results. Thank you for your attention.